Okay, my goal today is for you to walk out of here having learned a new integration technique. Okay, the technique is called U substitution. It's super handy, and through chapter 5, I would say, yeah, you can't integrate that yet. You don't know how, you don't have the skills to do it yet. I haven't taught you how to do that, so we needed to use Math 9. But now we're going to learn this new technique called U substitution. Super helpful in making our integrals more simple, to simplify our integrals and allow us to be able to integrate things we couldn't integrate before. So you'll hear me say throughout this chapter, have you thought about trying a U sub? Okay, U substitution, a U sub, it's going to be a really helpful technique. All right, so let's get into it. You need to become skilled at a couple things. Recognizing when U substitution is the best method, because right now the methods you have are geometry. You have methods of plain antiderivatives, like when is it a natural log, when is it an inverse trig, when is it those straight ones that you learned. And we had Math 9. Those were our 3. This is the 4th technique, this U substitution. So when is this going to be helpful? And then how do you apply it correctly? That's your kind of big view of what you need to do today. All right, so here's an example. Last chapter, the best way, or really the only way that you had to integrate this correctly is to use superfoil. So you would have taken your integral, and you would have taken x minus 4, and you would have multiplied it out 3 times, and then proceeded to the process of superfoil all those terms together. All right, so you probably would have foiled the first batch, which would give you this trinomial, and then you would have multiplied those terms together, and you would have had x cubed, and then minus 4x squared, and then minus 8x squared, and then 16x, and then 64. Oops, I missed one. X squared 4x. Oh, I missed the 32. 8x squared plus 32x, then plus 16x, then minus 64, and then dx. And then you would combine like terms, and you would integrate each term one by one. So there is a better way to doing this, and that's the process of U substitution. The biggest dead giveaway that U substitution is going to be like your great friend for the problem is if the problem is written with parentheses. So many times, if the problem has built-in parentheses into it, that means the U substitution is probably going to be your best way. So this one is going to be set up perfect for us. So here's the same question, and we're going to do it with a technique called U substitution. So what you do is you take what's inside the parentheses, and you reassign that to the value u. So I say u is going to be equal to x minus 4. Now this is a very basic example. I just wanted to get you kind of introduced to the idea. Then you take the derivative of that. The derivative of u is du dx. And we use Leibniz. Now we don't use Newton, we don't use primes, we use Leibniz because Leibniz works best with integrals, and so we're going to use that notation. Okay, what is the derivative of x minus 4? 1. Okay. Your next step is to isolate du by itself as a differential. Okay, du is the numerator, and I just want to get that by itself. So what do I do to that du over dx equals 1 to get du just totally by itself? Okay, so multiply, so that converts that to du being equal to dx. Okay, this is a very basic example. I'm just showing you how U substitution works. Then you go back to your integral. And you're going to do a double substitution. You're going to substitute in the parentheses, and you're going to replace x minus 4 with the letter u that you chose. You're also going to replace dx with what it's equal to. So this becomes, in the parentheses goes the u, and outside of the parentheses is the cubed. And then dx is going to get replaced, and I see over here that dx is equally replaced with du, and so I get du. So this becomes parentheses u cubed du. And then we find the antiderivative of that. The antiderivative of u cubed, we raise our power, u to the fourth. We divide by our new power. We add plus c. And then for our final answer, we switch it back. And we say the u had represented the quantity of x minus 4. So I go back to x minus 4 quantity to the fourth now, over 4 plus c. And that's the antiderivative using u substitution. Evan, question? Okay, this was a basic example. This may not have been the best way to do this problem. Okay, we could have done it with superfoil, but this is a way using parentheses. All right, let's go to the next one. So your rule of thumb, if it can be written with parentheses, then it's often, okay, notice it doesn't say always, but often integrated most easily with u substitution. Okay, so that's your look for parentheses first. Okay, so here's another one. Okay, we see our parentheses, cosine 5x minus 7. And we recognize that the parentheses contain 5x minus 7. So that most likely is going to be our choice for u. So kind of over to the side in the margin, you identify what you're choosing as your u. So we're choosing 5x minus 7. I find the derivative of that. So the derivative du dx, and the derivative of that is 5. Then I isolate the differentials. So du should get separated from dx. So like Matthew suggested, we multiply by dx. So I get du equals 5 dx. Now this is not a one-to-one equality like it was last time. Last time du and dx ended up to be completely equal to each other. I need to go one step farther here and find out what dx is by itself. So dx by itself is du divided by 5. So the substitutions I'm going to make are the original u substitution, and I'm going to make a substitution for dx being equal to du over 5. Now we come back to the integral. So that's like all the work you do. It's like pre-writing an essay, right? Coming up with your outline. It's the pre-work that you do. Now you come back to the work. Make an equal sign to announce that you're starting to continue the work process. And this will be cosine parentheses, and in the parentheses will go u, because that's what we chose u to substitute for. Then we replace this tailing dx. But this time it doesn't get replaced with just one du, it gets replaced with a du over the number 5. And because 5 is a constant, I can pull it out in front of my integral, which will leave me with cos u du. So if I pull it out front, if I take that 5, which is a constant, pull it out to the front, what does it really look like? It is. It's a 1/5. And now I find the antiderivative of this. So 1/5 bracket, my antiderivative of cosine is sine of u plus c. And then your final answer is to replace the u back to what you substituted or what you chose it to be. 1/5 of the sine of the quantity, 5x minus 7 plus c. Okay, this was still a problem you could have done last chapter. However, if you don't use u substitution, you have to remember the chain rule, the anti-chain rule. And I'll tell you, more than half of you in here forgot the chain rule at some point on your test. If you do u substitution, you'll never forget chain rule, because it forces you with this 5 that shows up right here. That 5 is what's representative of the chain rule that you maybe forgot. But if you do u substitution, you'll never forget it because it's part of the process. Yeah, Esther? No? Okay. So I always encourage u substitution because it's safer than having to remember the anti-chain rule, which is very forgettable. So let's try again. Remember, we're trying to see things in terms of parentheses. So I would encourage you first to rewrite this question using parentheses. Instead of using a denominator, instead of using a radical, rewrite it using parentheses. That should be your first pre-work. So this would become, instead of 1 over, it's going to come the quantity 3x plus 2. And then what will the power be on that? It'll be 1/2 to represent the radical, but what represents the denominator? Okay, we need -1/2 dx. So that's your pre-work. Parentheses are your friend. Rewrite with parentheses. Then choose your u, and your u is going to be 3x plus 2. Then we find our derivative. So du dx turns out to be 3. So we isolate the differentials. Du is equal to 3 dx. So dx is equal to du over 3. Again, this is all the pre-work that you do. Then you go back to your integral and you replace. So u is the quantity, and dx gets replaced with du over 3, which again tells me, oh, I can pull a 1/3 to the front. So I'll have a 1/3 in front of my parentheses, u to the 1/2. And then I do my antiderivative. So 1/3 bracket, and then this u will get raised according to the addition rules. So we'll take it and we'll raise it to the power positive 1/2, and then we'll divide or multiply by 2 and add c. And then your final answer would be replacing the u back to what it originally represented. So putting everything together, I have the 1/3 out front, I have the 2 coefficient, so I can write that as 2/3. And then I have parentheses, 3x plus 2 to the 1/2, or you can write that as the square root of 3x plus 2. Either way, your preference. And then plus c. Okay, so whether or not you write that with 1/2 power or radical is totally up to you. The only thing you can't do is you can't leave a negative exponent. Okay, Matthew first.
Wouldn't you distribute the 1/3 to the c also, so it's 1/3 c?
Okay, that's a really good question. Do I distribute the 1/3? Okay, c represents what?
Constant.
A constant. What happens when you multiply the constant by 1/3?
You divide the constant by 3.
Okay, and do you get, what kind of number will you get? Will it still be constant or will it be different? It'll still be constant. And so we don't have to indicate that because a constant is a constant no matter if I multiply or divide. It's still a constant. 1/3 times a constant doesn't change the fact that it's a constant. It's a different constant, but it doesn't matter. Our plus c isn't anything specific. It just represents a constant. It's not a specific constant.
So when you're trying to find something specific, would you then?
Okay, so if we had, and so that would be, you're thinking ahead to a couple lessons down the road. That would be when we had an initial condition where we'd have to find our plus c. Yeah, and then we'd have to put in the number like 1 and 5 or something, put something in and find our plus c. Yes, then you would. But this is a general constant. Okay, Meg?
That's the same question.
Great, great minds. Okay, let's keep going. So far we've seen one rule of thumb. If it can be written with parentheses, probably a prime candidate for u substitution. All right, when else does u substitution work? Okay, rule of thumb number 2. If it can be written as a product or a quotient, then it can be integrated most easily with substitution as well. Okay. You are allowed to add integrals. You are allowed to subtract integrals. You cannot divide 2 integrals. You cannot multiply 2 integrals. Several of you thought that you could do that. Okay? You can't. If you have a product, that's multiplication. You can't do integrals of that. You need something different. And that's why u substitution comes in handy if you have a product. So this is rule of thumb number 2. Look for a product. So here we go. Here's a product. It also happens to have parentheses. It's both. It's a product and it's parentheses. So again, your pre-work is going to be to rewrite this as 6x parentheses 1 plus x squared to the 1/2 dx. Now this is a lot more complicated because it has both a multiplication and parentheses in it. However, your choice should be pretty clear. When you make your u choice, choose what's in the parentheses. Okay? So we're going to choose u to be equal to 1 plus x squared. This is our pre-work. We find the derivative. So du dx equals, okay, what this time? Kristen? 2x. Okay, now isolate the differentials. So 2u equals 2x dx, but I have to take it one step farther. I need the dx to be isolated. So dx will be equal to du divided by, not a constant this time, but a constant and the variable 2x. Okay, that's our pre-work. Now we're going to go back to the problem and remember what we're substituting for. We will be substituting only what is in the parentheses, and we will be substituting for the differential of x on the end. Don't worry about the 6x. You're going to, if you can't anticipate and see it already, you'll see it in just a minute what's going to happen to it. So the 6x is fine to stay there. The parentheses will be my u to the half, and my dx is going to be my du over the constant 2 and the variable x. Okay, do you see it now? What's going to happen? Come on, look carefully. Yes, the x reduces. Okay, not just the x reduces, what else? The 6 and 2 reduces as well. So the 2x completely reduces into the 6x. And what will I be pulling out in front this time? A 3. And I will only be left with u to the half du. Everything reduces. In a product like that, everything should reduce. If something doesn't reduce, that means your u choice at the beginning was not the right u choice to make. Somehow you made a mistake in what you chose for u, so go back and try again. But it should always reduce. And then we can do our antiderivatives. So u now is to the 3/2, and we multiply by 2/3, and we add c. And we have another chance to reduce again, because the 3 that came out can reduce with the 3 in the 2/3, and I'm left with the coefficient of 2. And then I change u back, 1 over x squared to the 3/2 plus the constant c. And Matthew, we have that again, where that 3 doesn't need to be distributed because a constant is a constant. So in these products, or possibly a quotient, if you make the right u choice at the beginning from the parentheses, everything will simplify and reduce down to a very simple antiderivative. That's the beauty of u substitution, but it's all dependent on you choosing the u correctly at the beginning. And when you're just learning this first time on your homework, you're probably going to make mistakes on choosing your u, okay, the wrong u choice. And you may have to go back and try again. The first 3 problems of your homework tonight, the book identifies for you what the u choice is. They very nicely say, here's the problem and here's the u you should use. Okay, but after you finish 3 problems, then they're going to say, okay, you're on your own. So rule of thumb, always, if you can, if there's an opportunity, choose the parentheses. Okay, let's keep trying. So if that rule of thumb works, it should work here again. Okay, we have a product and we have parentheses. Both of those things tell me this is probably a u substitution choice. Okay, is there anyone who feels comfortable choosing a u? Matthew? Okay, great choice. 2x squared. We apply derivatives to that. So du dx will be 4x. We isolate and we get 4x dx. And then we isolate dx by dividing du by the constant 4 and the variable x. There's definitely a rhythm to these problems. You'll start to see it kind of feel very repetitive, the same steps each time. So now we're ready to go back. Please develop good habits right now of using equal signs to connect each step of your work, making sure you continue to use parentheses correctly. Okay, We are substituting now, not for the x out front. Okay, we don't worry about that x that's sitting right there. We are only substituting for what is in the parentheses, and we're substituting for the differential. And as we hoped, there's reducing to happen, and the x's can fully reduce, leaving me with a constant to pull out to the front. And so I'll pull the 1/4 out, and I'll be left with the sine of u, quantity, and then du. So it always should do that. Then you're ready for a pretty simple antiderivative. The antiderivative of sine is negative cosine. And then we just have to swap the u back out for what we substituted for. So we'll have negative 1/4 of the cosine of 2x squared plus the constant c. Any questions on that one? All right, let's just see a few more things for practice. The best u, here's another rule of thumb. Okay, if you don't have parentheses that make it obvious, okay, choose one whose derivative is present. What's a better way to say this? Choose the higher power. If you have multiple things to choose from, choose the higher power. Okay, why is a higher power a good choice? Okay, Matthew, you have an idea about that? Okay. Yeah, Esther.
It makes it less complicated later on solving for the antiderivative.
Okay, it does. And what happens is when you make your u choice, what are you doing to that u? What's the first thing you do to it? Take the derivative. What will a derivative do to the thing that you chose? It's going to lower the power, right? Okay, and chances are when it lowers the power, it might reduce the other thing that was sitting in your equation to begin with, all right? So choose the higher power. Okay, so here's a sample of that. Here's a multiplication problem where we have x squared and we have e to the x cubed. Now we don't have any parentheses to help us choose, but we do have two variables of different powers. We've got x squared in the front and we've got x cubed as a power. And so the choice here would be to choose that higher power. Choose x cubed, not the e. E is a constant. We don't need to choose that, but we'll choose the x cubed. So what that will do then is when I take its derivative, it lowers that power to 3x squared. And we start to say, if I lower the power to 3x squared, I can anticipate that there might be some reducing that's going to happen. So 3x squared dx. And we work toward isolating that dx. And we get du over 3x squared this time. Again, so that's all your pre-work. Make sure that's somewhere, some people, a strategy will be to like put a box around that, to show it's not really it's part of the process, but it's not part of your problem. Your problem is the equal part that continues. So that's one other strategy that you'll see people do. So again, the x squared, I'm just leaving there. I don't need to touch that. The e, but it was the x cubed that I chose that becomes my u. And my dx becomes du over 3x squared. And so now we have, okay, great, that extra x squared. I was patient with the x squared. I didn't worry about it because it's going to reduce, leaving me with the constant to pull out to the front. So 1/3 gets pulled out of e to the u du. And now you have a simple antiderivative. And e to the u's antiderivative is also e to the u, but it has the rule where you have to divide by the natural log of e and the chain rule of 1. Evan and Meg.
So, if you take the derivative of when you're doing the antiderivative of e, you take the derivative of e's exponent.
Because u was the only thing I chose for u was x cubed. I didn't choose the e as part of that choice.
Yeah, so then
No, we've switched over. U is just its own variable. U is a single. I'm not switching back to x terms anymore. It's just the derivative of u is 1. Just like if you were working with the derivative of x. Meg?
That was my same question.
Okay. God, you guys are thinking so great. The reason we switched to u is that we didn't have to use x's anymore. So u is its own thing, and it has its own derivative of 1. Okay, so this gives us 1/3, and then e to the, and now that is x cubed plus c. Okay, how you doing? Any other questions so far? It's great that you're thinking of things as you go. Okay, now I know this next one looks horribly confusing, but the u substitution is going to make it great. All right, so first thing we should do is switch it to parentheses, okay? So your pre-work should be to put cotangent in parentheses of 1/3 and cosecant in parentheses and then dx. Okay, now comes your chance to choose your u. Okay, anybody want to make a choice? Okay. All right, we're choosing cosecant. So when we do our derivative on cosecant, what is the derivative of cosecant? Negative cosecant x cotangent x. Think ahead to some isolation. Okay, if we pull this out, and we have the dx, and then we get dx alone, dx is going to be du over negative cosecant x cotangent x. As you look at that dx, that was the result right there, and you think kind of ahead to, I'm going to put this right here, because that's where it's going to go. Will it fully reduce the thing that I didn't choose for you? It'll partially reduce it, but it's not going to fully reduce it. If it's not going to fully reduce what you didn't choose for you, then it probably wasn't the right choice for you. It should fully reduce it, not just partially, because if we could partially, but it's just going to make it messier. So sometimes it's okay, I let you choose maybe not the right u to begin with, so that we can go back and we can learn, all right, then how could I pick something different? So we're going to just go back and take another stab at it. Oh, well, choosing cosecant wasn't the right choice, so can we choose the other thing, which would be cotangent? So let's try that. Okay, choose cotangent. All right, what's the derivative of cotangent? Is it? Negative cosecant squared of x. And so then when we do our isolation on that, we're going to get dx equals du over negative cosecant squared x. And if you think ahead to substituting that, will that fully reduce the other part that you didn't choose? And the answer, if you can see it, is yes. So we have u to the 1/3, which is what we chose. We didn't choose cosecant x squared, and then the du, the differential, is negative cosecant squared of x. So that is a better choice for us, because everything fully reduces except one thing. What's the only thing that doesn't reduce? Well, no, not the u, there's something else. The negative doesn't reduce. And so we can reduce here the cosecant squareds, but the negative doesn't. So we'll pull the negative out to the front, and we're left with u to the 1/3 du, and that's all we're left with. So even that super complicated thing that we started with, we're down to a very simple integral. So the antiderivative would be negative u to the 4/3 times 3/4 plus c. And then we change our u back to what we chose it to be. So negative 3/4 parentheses cotangent of x to the 4/3 plus the constant c. Juliana? Okay. All right, last rule of thumb. Okay, our first rules of thumbs were looking for parentheses. Okay, looking for a product, choosing the higher power if you had multiple choices. Okay, multiple things to choose from. And then the last one is, you know what, it might take a trig substitution. All right, so here we go. This really does not look like much. Like seriously, cotangent needs a u substitution? Well, yeah, cotangent doesn't have a nice antiderivative. Okay, you got to remember, cosecant cotangent has a nice antiderivative, but cotangent itself doesn't. So try a trig substitution. What is cotangent as a defined thing? What is cotangent equal to in trig? Okay, so try that first. And we'll have cosine of x over sine of x dx. Well, now at least we have more things to work with. And we can choose a u from that. When you end up with a denominator, if I was making rule of thumb number 5, this would be rule number, choose the denominator. Okay, if you have a denominator and all other things, like you don't have parentheses or anything else to tip you off, choose the denominator, sine of x. Because what is the derivative of sine of x? Okay, and so you can see, oh, it's cosine of x, so I'm going to be able to reduce out the cosine of x that I had. So we isolate, and we get our differential alone. And then we go back, and our pre-work is done. So we chose the denominator as u. We did not choose the numerator, so the numerator still has cos x in it. But the differential was du over cos x, which fully reduces. I have no constants left to pull out. What I am left with is 1 over u du. And that has its own special antiderivative, doesn't it? What is the antiderivative of 1 over u du? ln. ln absolute value of u plus c, which would then be the ln of the absolute value of sine of x plus c. And that was our final example.